So today we are going to solve one of the easier problems of Leetcode, which is called twosum. Let's read the description and go through certain examples in order to understand the problem first. Given an array of integers nums and an integer target, return the indices of the two numbers such that they add up to the target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So let's go through some examples. In the first example, we have the numbers array, which contains 2, 7, 11, 50, and 15, and a target of 9. And here our output should be 0 and 1, because if you add up the number at the 0th and the first index, 2 and 7, you will get 9. In the second example, we have the numbers 3, 2, and 4, and our target is 6. And in this case, we need to return 1 and 2 because the numbers at the first and the second index, which is 2 and 4, if we add them, we get 6. And in the last example, we have the numbers 3 and our target is 6. And if we add them up, we get 6. Let's consider the following example. We will come up with a brute force solution first and then optimize it later on. An obvious solution here would be to iterate through the array twice, and at each iteration add the two numbers and then compare it to the target. So let's initialize a variable I on the 0th index and a variable j on the 0th index as well. And at this point we cannot add the same number two times, so we skip this iteration and go to the next iteration. And at this point we have 2 and 7, and we just add them up, which is 9, and we compare to the target. At this point we have not reached our target, so we continue with the iterations. So j would be 2 in this case, which is 11, and then we add 2 to 11, which is 13, and compare to our target with 18, and it doesn't equal to the target, so we continue with the iterations. J would be 3, which is 15, and we add 2 to 15, which is 17, and still we have not reached our target, but we've reached the end of the array. So what we do at this point is reinitialize j at 0 and increment I to 1, and then start again. So now we have 2 and 7, we add them up, which is 9, which does not equal our target, so we continue with the iterations. And at this point we've ended up at the same number, so we skip this iteration, and j would be 2. So now we have 7 and 11, and we add these numbers together, which is 18, and at this point we have reached our target, so we can return the indices, which is 1 and 2, and this is our answer. It turns out that this algorithm runs in big O of n squared time complexity, because we have two for loops and a constant space complexity. So let's code our brute force solution. We start with a for loop, rise less than the length of nums I++, and inside the for loop we create yet another for loop where j is less than nums length j++. Remember, we can only use the same element once, so we need to check if we are at the same index. If that's the case, we can just continue with the iterations, and otherwise we can just grab the number at the ith index plus the number at the jth index and check if that equals the target. If that's the case, we can just return the indices. So let's run our code, and it succeeded. This code will run in O of n squared time and in constant space complexity. It turns out there's a better way of solving this problem, which involves only one iteration through the array. At each iteration, we just calculate the difference between the target and the current number and store the result in a dictionary. At a later iteration, if we happen to find that number, we can just return the indices. So let's initialize a variable I for the iteration and another variable dictionary in order to store our calculations. And then at the first index, or the 0th index, we calculate the difference between 18 and 2, which is 16. And then we store 16 in the dictionary with the current index. So if we happen to find the number 16, we should return 0 along with that index that we are at that moment. So let's continue the iterations. So now we are at index 1, which is 7. We calculate the difference again, which is 18 minus 7 is 11, and we store 11 in our dictionary, which is along with the index 1. And then we continue our iteration, which would be 2. And at this point we are at index 2, which is the number 11, and we check the dictionary. Does 11 exist? Yes, it does exist, which returns index 1. So we can return 1 and 2, which is our answer. It turns out that this solution runs in big O of n time as well as big O of n space complexity. So let's go to the optimal solution. First, let's instantiate a dictionary, and then we create a for loop. Right, less than length of numbers plus. Within the for loop, we calculate the difference between the target and the current number, and then we check if the difference is inside the dictionary, if we have saved it before. If that is the case, we can just return the index that is stored at the key of the difference and the current index. If that's not the case, we can store at the key of the current number the current index. Let's run our code. It succeeded, and this will run in O of n time and O of n space complexity, because we are utilizing a dictionary.